Hey everybody, it's Tuesday, February 9th, and as you can see here in the aim today, our goal for today's video is to apply the concepts of force and impulse that we learned about yesterday to collisions. So just as a brief summary, yesterday we said momentum is a measurement of how hard it is to stop an object, and that the properties an object has that determine how difficult it is to stop that object are its mass and its velocity. So mass and velocity determine the amount of momentum is possessed by an object. Now, we also said that when we are talking about how hard it is to stop an object, that there are two things that go into that. The first is the amount of force you have to apply in order to make the object stop. And the second is the amount of time you need to apply that force for in order to bring the final velocity of the object to zero. And so that brought us all to the idea of impulse, because when you are applying an impulse, or in other words, when you are changing the momentum of an object, you are applying a force to that object. That's the point. And so when you apply a force on an object, you, as we say, deliver an impulse and you change the momentum of an object. So we sort of also took a look at redefining force as being equal to the time rate of change of momentum. And if force is equal to the time rate of change of momentum, and if impulse is defined as the change in momentum, then we can see the relationship between impulse and force. And so, right, because impulse is just delta p, and force, we're saying, is delta p divided by time. And so that means impulse, which is the change in momentum, was just the product of the force and time, which should have, it should have made pretty clear that that was, fits in nicely with what we said about how hard it is to stop an object. Force and time are the key ingredients. And so now that we know about impulse, momentum, and forces, and the relationship between those, we can now sort of extend that idea to collisions. And so we're going to sort of start slow and then really get into some complicated problems. And so there's not really a whole lot to say here at first. Let's just take a look at a problem. This problem here says an estimated force versus time curve for a baseball struck by a bat is shown in figure P6.8. From this curve, determine A, the impulse delivered to the ball, and B, the average force exerted on the ball. And so we have a problem. And the problem we have here is they are asking us for the impulse. And the impulse generally is easy enough to find. There are three equations, and so you need to pick which one fits the data you have best. And the equation that fits the data we have best here is the equation for impulse that tells us to multiply the force and the time. Now, the problem with that is the force is changing, if you notice. And so because the force is changing, we can't just plug one number into that equation. We have a little bit of an issue on our hands. So there are a number of ways to do this problem, but ideally, we would like to be able to find a method that will enable us to find the impulse using the graph. And if we take a look at this graph here, noticing that we have force on the y-axis and time on the x-axis, there is a graphical technique that we have discussed a lot so far this year that it should be obvious is what we have to use here to find the impulse from this graph. How do you get force times time from this graph of force versus time? You find the area under the curve. So to start off this problem, let's write a note here. The area under the curve of a graph of force versus time is equal to the impulse, or change in momentum, since the units of the area under the curve are Newton seconds or kilogram meters per second. So whenever you have a graph of force versus time, and it doesn't really matter what the shape is, we'll just draw a straight line here. The area under the curve, the shaded area here, is equal to the impulse. That is something that is going to come up on the AP test a lot. So take a second to pause this video here and write that down. And when you hit play, we'll take a deeper look into that problem. All right, so looking at the information presented in this problem here, we can see that the area under the curve is going to be the area of this triangular shape, right? And every single year, I think it seems to me like a lot of people don't quite recognize two things about this problem. The first thing they don't recognize is that, yeah, while this is like a sort of weird looking triangle like this and not a right triangle like we usually deal with in these graphs, the area under the curve of any triangle, including this one, is 1/2 base times height. You could, if you really wanted to, just find the area of this triangle, then find the area of this triangle, and then add them up, but that's a waste of time. Don't do that. The other thing a lot of people fail to realize, it seems, about these kind of problems is that the area under the curve here can't be calculated unless you convert the units on the x-axis to seconds. This is a prefix. The prefix is milli, and milli stands for 10 to the negative third. So this, taking place from 1 to 2.5 milliseconds, needs to be adjusted before you go ahead and solve the problem. So this is not your first rodeo here with the areas under the curve. So y'all should know how to do this by now. Take a second to pause this video here and finish at least part A. And when you hit play, we'll go over part A. So according to this graph, the maximum force exerted on this baseball by the bat is 18,000 newtons. So that means the height of our triangle here is going to be 18,000 newtons. The base of the triangle, remember, goes from 1 to 2.5 milliseconds. So 1 to 2 is 1 millisecond, 2 to 1/2 is another 1/2 millisecond. Oops. So that will be 1.5 milliseconds, or 1.5 times 10 to the negative 3 seconds. And our area under the curve here, the total area, is going to be equal to the impulse. And since this is just one triangle here, the area calculation is pretty straightforward. We have the total area under the curve is equal to the impulse, and that's 1/2 base times height. And so the total area, which is equal to the impulse, is 1/2 of the base, which is 1.5 times 10 to the negative 3 seconds, times 18,000 newtons. And so when we plug those numbers in and we do that math, we end up getting 13.5 Newton seconds. Notice if you forget to convert that unit, you end up getting an answer which is measured in units of Newton milliseconds, which is not an appropriate unit in this system of units. Now, to take a look at part B, before we move on, part B of this question is asking us what is the average force exerted on the ball. Now, looking at the numbers in the graph, it might not be that hard for all of us to just guess what the average force is going to be, or to really make a good educated guess about what the average force would be. But really, what they want us to do here in order to calculate the average force is use this equation for impulse that we developed yesterday. So we just calculated that the impulse is 13.5 Newton seconds. We also saw that the time is 1.5 times 10 to the negative 3 seconds. And we're looking for the net force. So according to the equation that we developed yesterday, J is equal to F net times T. And so that means F net, according to that equation, is J over T. And so pretty simply here, we have F net equals J, 13.5 Newton seconds, over a super tiny number here, 1.5 times 10 to the negative 3 seconds. And when you do that math, plugging in all the numbers appropriately, you end up getting 9,000 newtons. Now, of course, this number should not come as a surprise. And the reason why I think this number should not come as a surprise is because notice the force is increasing and decreasing linearly. It increases from 0 to 18,000. And so that means the average over the first part is 9,000. And then it decreases linearly from 18,000 back to 0, meaning the average on this part is 9,000. And so the average over the whole thing is 9,000. It would be the same thing. And that's the idea. Notice, we could also confirm that that really makes sense geometrically, because if instead of having a triangle that looked like this, if instead our area under the curve was just a constant 9,000 Newton force, we would have our area under the curve look like basically this rectangle here, whereas, wherein these shapes, this triangle and this triangle, have an area which is equivalent to that triangle, and that's why the areas end up being the same. Take a second to pause this video here and write that down. Fix any part of your calculation that might have been missing, or just copy it if you didn't get a chance to write that part. And when you hit play, we'll move on. So believe it or not, it's actually a really, 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 really important thing for the AP test that you know and understand that the area under the curve for a force versus time graph is the impulse or the change in momentum. But of course, there are other physical quantities we can graph force against. In other words, we could graph force against time on a graph that looks just like the one we saw in that problem, but we can also graph force against displacement. And I find it to be kind of weird because to me, it's very easy to tell the distinction between these two things. But on the AP test, they love to ask you what are, in my opinion, really basic questions about the difference between the force versus time graph and the force versus displacement graph. The force versus displacement graph, if you notice, has units. Remember, 1/2 doesn't have a unit here. So it has units of Newton meters. And so the force versus displacement graph has an area under the curve that represents work. That should make sense. Work is force times displacement. Or you can write it like this, F delta x cosine theta. Whereas for the force versus time graph, which notice here is once again a triangle where the 1/2 doesn't have units, the unit for the base is seconds and the unit for the height is newtons. And so we'll just write Newton seconds like this. And so that means the area under the curve is the impulse. And so they love to ask these kind of questions to ask you to make this basic distinction. And that's an important thing to recognize. What I think is important to recognize even further, though, because then you can use this to really do some good experimental design thinking, is that a graph of force versus displacement or force versus time is really useful for experimental thinking, because it's important to realize through the work energy theorem and the impulse momentum theorem, you end up getting an equation for impulse that has the final velocity of an object in it. And you end up, if you use the work energy theorem, saying that work is equal to the change in kinetic energy, you end up getting an equation that has the final velocity in it. And so it's an important thing for everybody to recognize that these two ideas are fairly similar in style and structure. Impulse is equal to the change in momentum. Work is equal to the change in energy. And if you're just pushing an object horizontally on a surface, then it will be equal to the change in kinetic energy. And if we know the change in kinetic energy, and we know the mass of an object, and we know its initial velocity, then we can find the final velocity. Similarly, for the impulse argument, if we know the impulse imparted to an object, and we know the mass of the object, and we know the initial velocity, then we can find the final velocity. That is the key detail. And so a good note here would be both of these graphs can be used to determine the final speed of the object. If the initial speed is given or the object starts from rest and we have the mass, I promise you, you will see questions on the AP test and so eventually on our tests where you are asked about this difference and similarity between these two kind of graphs. I'd like you to take a minute to pause this video here and make sure you have these graphs written down along with all the other additional information we wrote on this slide and this note. And when you hit play, we'll move on. Okay, so just so we have everything down here in an extremely clear way, because like I said, they really drill down on this on the AP test. I want you to write this under the heading graphing techniques. You don't have to write anything that's in bold. You just have to write what is not in bold. The question here is, how can we use graphing techniques to determine the work done on an object? Since work equals force times displacement, I didn't feel like putting the delta and the x in there, so I just wrote d. You can write F delta x cosine theta. The work can be determined by calculating the area under the curve for a force versus displacement graph. That's very important to know. Next question, how can we use graphing techniques to determine the impulse delivered to an object? Since J equals F net times T, the impulse can be determined by calculating the area under the curve for a force versus time graph. Super important. It's also a clutch thing to have in your back pocket for experimental design questions, because if they say, there's a force exerted on this object, we want to find out its final velocity. If you have a force sensor, like how can you do it to get the final velocity without just using a motion sensor? There are a lot of ways you can do it. You can make a graph of the force versus displacement and go the work energy theorem route, or you can make a graph of force versus time and go the impulse momentum theorem route. There's a lot of versatility in your experimental design capabilities and techniques if you really get this distinction down. I'd like you to take a second to pause this video here and write that down. And when you hit play, we'll move on. Last point about these graphs. I just want you to have this down. If we ask the question, how can we use the work to determine an object's final speed? The work is equal to the change in kinetic energy. And if you take that equation, work equals 1/2 mv final squared minus 1/2 mv initial squared, and you solve it for the final speed, you get that, right? We can factor out the 1/2, multiply both sides by 2, divide by the mass, and then add the initial velocity to the other side. So that's how you can go ahead and do this. I guess I'll show all that work over here. So we'd have 1/2 m v final squared minus v initial squared. And so we'd have 2w over m is equal to v final squared minus v initial squared. And hopefully you can see it from there now. We'll add the v naught squared over to the other side, and then we'll take the square root. Now, of course, we could also ask, how can we use impulse to determine an object's final speed? Same thing. Since j equals delta p, we can use the equation vf equals j over m plus v naught. And once again, here, it's just by saying j equals mv final minus mv initial. And we can factor out the mass. So we have m times v final minus v initial. And then that gives us j over m equals v final plus v initial. Sorry, v final minus v initial. And then, of course, you can see where that's going the rest of the way. You just add the v naught over to the other side, and you're in business. Now, I know that might have seemed annoying because I just said all that stuff and then I asked you to write down all that stuff separately. This is a really important thing they're looking for on the AP test. I really want to make sure everybody has this down. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So now we're going to get into the part of the lesson where we sort of shift gears here, and we start talking specifically about collisions. Now, technically that last problem was a collision. It was about how a baseball bat collides with a baseball. But that's really sort of an active and applied force that's being exerted by the bat onto the ball. And so it's kind of a collision, but also kind of not. Regardless, here we're going to be talking about collisions in contexts that don't really involve graphs. And so we're really kind of looking to shift gears here in a fundamental way. And so we want to make sure that we are able to describe this carefully and in great detail. The first question we're going to ask, which may be a stupid question to ask, but still is important nonetheless, is what is a collision? What is a collision? And so we can say here, well, a collision is any event during which two objects exert forces on one another. That's very important. A collision is any event during which two objects exert forces on each other. Well, now we can ask, how do laws of physics that we've already learned apply to a collision if a collision is an event during which two objects exert forces on each other? If we want to be really obvious about the way we're asking that question, we could just say, what do we know about those forces that those two objects exert on each other? And pretty simply here, we can say, since the objects are in contact, two objects are in contact and exerting forces on each other, Newton's third law applies. That's pretty straightforward. And as it turns out, the fact that these two objects are in contact with one another and are exerting forces on each other and Newton's third law applies is a remarkably important idea for us being able to understand why we are about to do the things we're about to do. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Moving on, there are a couple of important things we need to say. According to Newton's third law, as you should already know, when objects are involved in a collision or exert forces on each other in general, they will always exert equal and opposite forces on each other. Always. No matter what. Now, of course, the word in this big sentence that is most important, I think, is always. Now, whether you realize it or not, the reason why that word is incredibly important is because if we have two objects here and we say object A, let's just say this object is object A exerts a force on object B for 10 seconds, but object B only exerts that same force on object A for 9 seconds, then during that last second, they're in violation of Newton's third law. The point is, if object A exerts a force on object B for 10 seconds, then object B has to exert a force on object A for the same 10 seconds. Now, why am I talking about that? Why does the fact that not only is the force the same, but the times are the same too? Well, if the forces are the same and the times are the same, and the product of force and time is impulse, then that means the impulses are going to be equal and opposite too. So because the forces have to be equal, the time interval during which those forces are exerted on each other has to be equal as well. And when objects exert equal and opposite forces on each other, each object will receive an equal and opposite impulse. Super important. So important, in fact, that it's taking up the whole space on this whole slide. I'd like you to take a second to pause this video here and write down this note and this note. When you hit play, we'll move on. Okay, and so that brings us to, honestly, one of the more important concepts in this course, which is conservation of momentum. Momentum is a conserved quantity. Really, this is one of the main reasons why we talk about momentum. Now, we talk about momentum because of its relationship with force, for sure, but because of momentum's relationship with force, specifically because when two objects are colliding, the forces they exert on each other have to be equal and opposite, and the impulses are equal and opposite, it means the objects will always experience equal and opposite changes in momentum. And the key detail here is that if each object has its momentum changing by the same amount, but in opposite directions, meaning if one object has a momentum change of plus 10, the other has a change of minus 10, then the total between them is always the same. That's extremely important because some objects will lose momentum in these collisions, and other objects will gain momentum in these collisions. But the total amount of momentum possessed by these objects will be the same because the impulses are equal and opposite. Super, super, super important note. Momentum is conserved, which means the value for the total momentum will never change. This is true because the equal and opposite forces the object exert on each other will produce equal and opposite changes in momentum or impulses for the objects, which ensures the total momentum will always be the same value. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so let's go ahead and show how we can come up with the equation for conservation of momentum. This should probably say conservation of momentum derivation. So let's say we have two objects. We'll call this object object 1, call this object object 2. We're going to have object 1 with a mass of m1 and object 2 with a mass of m2. This object is going to be moving at a speed we'll call v1. This object is going to be moving at a speed we'll call v2. This is the before image. They collide. Then after, object 1 is going to be moving back this way with a velocity we're going to call v1 prime. Notice v1 prime here makes sense for the symbol for velocity after, because remember, we used the symbol prime already to mean like new. like new force or the force after the changes are made. So that sort of fits in with that framework. And then we'll just say object 2, maybe, not always, but maybe in this particular example is just coming back this way with a velocity of v2 prime. And so we start here with the impulse momentum theorem. And so let's start with object 1. Well, object 1 experiences a force from object 2 on object 1. And that force happens for a certain amount of time. And according to the impulse momentum theorem, the impulse, force times time, is equal to the change in momentum. And so the change in momentum is always final momentum minus initial momentum, right? So the final momentum would be m1 v1 prime minus the initial momentum, which is going to be just m1 v1. So there is the application of the impulse momentum theorem for object 1. For object 2, now it receives a force from object 1 on object 2. And that force happens for a certain amount of time, right? And we can say that's the impulse, and that's equal to the change in momentum, where the change in momentum is the final momentum, m2 v2 prime, minus the initial momentum, m2 v2. And that's our basic application. Now, the third law mandates that F21 is equal to the negative of F12, and that the time, let's just say for 1, is equal to the time for 2. And so essentially that means these two things are equal, this product and this product. And if these two things are equal, then that means the equations for these two things are equal. And this ultimately is where conservation of momentum comes from, because what we're saying then is F21 times t is equal to F12 times t, but with a negative sign. And so what we end up getting is m1 v1 prime minus m1 v1. Notice that's just our equation from here. And then we're going to have the negative of our equation over here, m2 v2 prime minus m2 v2. And that's the deal. And so now if we just rearrange our terms here, making sure we distribute this negative sign, we have m1 v1 prime minus m1 v1 equals m2 v2 prime is going to end up being a negative term, and m2 v2 is going to be a positive term, because negative times a negative is going to end up making a positive. And so notice here, we can sort of group our terms in an interesting little way. If we add m2 v2 prime to both sides, now we have m1 v1 prime plus m2 v2 prime. And if we add m1 v1 to both sides, now we have our positive m1 v1 and m2 v2 on one side, and our positive m1 v1 prime and m2 v2 prime on one side. And so we can say m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. And that is conservation of momentum. Because notice, this term is the initial momentum of the system, and this term, or I should say those two terms, is the final momentum of the system. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So that, in general, is our basic conservation of momentum equation. Now, I want to be very specific about how this equation works, the terms, et cetera, et cetera. Now, you can always start off, if you want to, with a simple statement of conservation of momentum, which is that the initial momentum, P naught, is equal to the final momentum, P final. Now, in general, in this course, we are going to be seeing problems where we have two objects involved. And if that's the case, or when that's the case, the conservation of momentum equation is going to look something like this. So we have m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. Essentially what this equation is saying is if the initial momentum is equal to the final momentum, we take the initial momentum of object 1, the initial momentum of object 2, and we say that that's equal, once they're added together, to the final momentum of object 1 plus the final momentum of object 2. Now, This, of course, is an equation with 6 different symbols in it. So let's just be clear about what those symbols are and mean. M1 here, of course, is the mass of object 1. V1 is the initial velocity of object 1. M2 is the mass of object 2. V2 is the initial velocity of object 2. V1 prime is the final velocity of object 1. And V2 prime is the final velocity of object 2. This is almost always going to be like the master equation for conservation of energy, or excuse me, conservation of momentum that we're going to use. And so this is a very important thing to be very familiar with. Take a second to pause this video here and write that down. When you hit play, we'll move on. Now, there's one really important detail that we haven't mentioned yet that's important not to overlook here, because we have right now been a little sloppy about using phrases like when the forces are equal and opposite, the momentum will always be equal and opposite. And of course, always is a little bit of a sketchy usage of that word here. And so we should say, well, just like energy is not always conserved, sometimes momentum is not always conserved. And so the basic idea here is try to think of situations when energy is not conserved, and then think about why it's not conserved. When energy is not conserved, what happens? Why does that make sense? Well, as we say, energy is not conserved when there is external work done on the system. That makes sense because work changes energy. The question here is, what changes momentum? And as we've said, since the definition of force is the time rate of change of momentum, forces change momentum. And so we can say here, since forces change momentum, momentum is only conserved in a system in the absence of external forces. This is an incredibly important note. We can also say here, this is similar to how energy is only conserved in the absence of external work, because work changes energy. Take a second to pause this video here and write that down. These are 2 extremely important notes. And when you hit play, we'll move on. We're only going to take a look at one conservation of momentum problem today, and that's because it's a fairly simple and straightforward problem, generally referred to as the explosion problem. In an explosion problem, the objects start together. They push off of each other, of course with equal and opposite forces, and move away from each other. Mostly, they're initially at rest. Since they push off of each other with equal and opposite forces, the impulses delivered to each object are equal and opposite. We'll actually just go ahead and make that a comma here and say, so the momentum is conserved. That's the whole point here. Take a second to pause this video here and write this down. And then we'll just go ahead and jump right into an example to wrap it up for today. So let's take a look at one example here before we wrap it up for the day. This problem here says a 75 kilogram fisherman in a 125 kilogram boat throws a package of a mass of 15 kilograms horizontally toward the right with a speed of 4.5 meters per second, as in figure, whatever, that figure shown below. It says, neglecting water resistance and assuming the boat is at rest before the package is thrown, find the velocity of the boat after the package is thrown. And so, as is the case for energy problems, we're going to want to consider the objects present in the system here. And the objects present in the system here are going to be the man-boat system. They're really connected, and so that's what we're interested in. And then the package. Since the man part of the man-boat system, they're basically just connected, exerts a force on the package, and the package exerts force back on the man. Those forces are equal and opposite. Newton's third law applies, and so conservation of momentum applies. So let's go ahead and solve this problem. Now, the first thing I'm going to write down is going to look kind of weird because we have to deal with the fact that the fisherman and the boat are like connected. And so effectively we treat them as one object here. So what I'm going to write here is M1A is 75 kilograms. That's the mass of the fisherman. M1B is 125 kilograms. That's the mass of the boat. And so that just means the M1 that we're going to be using in this problem for the man-boat system is 200 kilograms. M2, the mass of the package then, is 15 kilograms. Now, if you look back at the situation in the problem, The problem says assuming the boat is at rest before the package is thrown. So the man-boat system is at rest in the beginning. But what about the package? Well, it's important to realize before the package is thrown, like if the person is winding up to throw the package, their arm is back here, and the package is in their hand, at rest. And so that means here, as we said, traditionally both objects are at rest. That means V1 is equal to 0 meters per second, and V2 is equal to 0 meters per second. Now they tell us at the end, the package is thrown with a velocity of 4.5 meters per second. Now it says here that's the initial velocity, but as far as the conservation of momentum interaction is concerned, that's its final velocity. Also notice because it's to the right, it makes sense that we keep it positive, and we're looking here for V1 prime. Now, we could start off with a simple statement of conservation of momentum that looks like this, but that, as far as calculating, is mostly going to be useless to us. We can write it just to like drive home to the idea to the person who's grading our AP test that like, yeah, we know momentum is conserved. We're not just writing this equation down from memory, but this is really going to be the equation that works for us here. Now, the crucial thing to realize, the nice thing about an explosion problem, is that when the objects start from rest, M1v1 and M2v2 are 0. And so that means effectively we just have 0 equals M1v1 prime plus M2v2 prime. Notice what that equation is effectively saying is there's 0 momentum present in the system. Now there's a couple of things for you to realize here about these problems. If there's 0 momentum in the system initially, because both of the objects are at rest, that means there's 0 momentum in the system at the end. But wait, you might think. If there's 0 momentum in the system at the end, how is it possible that either of these objects are moving? Because if they're moving, they have momentum, right? Well, if they're moving individually, they each definitely have momentum. But we are not really all that concerned with their motion individually when we are talking about the total momentum here, because we are considering both of them to be the part of a system. And the momentum of the system here is going to be 0. And what that tells us about the momentum of each object is that the momentum of these objects are equal and opposite. And so when we solve this for V1 prime, we get M2 V2 prime over negative M1. Just in case you didn't realize this point here about them having momenta at the end that are equal and opposite, the point is the impulses are equal and opposite. And so that means their momenta changed by the same amount, just in different directions. And that makes sense here, because they get forces in different directions. They speed up in different directions. And so if we plug in the numbers here, we get M2, 15 kilograms, times V2 prime, 4.5 meters per second. And then we divide that by M1, of course, with the negative sign out there just to take care of the direction, and that's 200 kilograms. And when you do that math, plugging in all those numbers and making sure you're doing the division correctly, you get negative 0.3375 meters per second, which we can just call negative 0.34 meters per second. And it's important to realize as we wrap this up for today, how much that answer makes sense. These objects experience equal and opposite forces. That's what a force analysis tells us. It's important to realize, though, right after we do that forces analysis, we jumped into the conservation of momentum thing. That doesn't mean the force analysis that we could do ceases to exist here. It's important to realize that Newton's first and second law still totally apply to this problem. The man-boat system has more mass, so it has more inertia. That means it's harder for the mutual force that's exerted between the man and the package to accelerate the man and the boat. And that, of course, is why they end up with a much smaller velocity. It's also important to realize that if they have the same final momentum, which they do, then the object with more mass should have less velocity because the product of the mass and velocity has to be the same number. And of course, that is the case here. This is a perfectly good and reasonable example of a classic explosion problem. And we will continue to circle back to this kind of problem as we continue to advance the ball forward, as we do some practice with conservation of momentum. But with that, that's it for today. Have a good one, everybody.